Were you at OFC this year? You must agree that since the telecom bubble burst, we have not seen such levels of energy. Data centers are driving the success of the photonics economy today. Days before OFC, Jensen Huang shocked the world by announcing everyone from investors to people in the street, from supply chain partners to politicians, that Silicon Photonics was critical for implementing AI. That move is not by NVIDIA alone. You saw recently the announcement of AMD acquiring one company from the Optica ecosystem, Enosemi, and I can anticipate that this is the beginning of many other investments and M&As. Manufacturing co-packaged optics the way NVIDIA announced it is not yet obvious and requires collaboration within the photonics supply chain. So on Tuesday, June 10th at 10 a.m. Eastern, 4 p.m. Central Europe, join Optica's expert panel as we tackle the key question: when do CPO become not just viable, but inevitable? We'll cover challenges in packaging, co-packaged optics readiness, and collaboration required to succeed, in a discussion led by Microsoft and AMS Osram looking for partnerships in their CPO roadmap. Our corporate members will have a chance to show what they can do to help. For example, with the micro-LED sources of Avicenna, the multi-material nano 3D printing of Heteromerge, the micro-optics manufacturing of Femtoprint, the design support of ANSYS, and OptiWave, the testing capabilities of Quantified Photonics, the record speed of New Photonics, the vertical integration of Axelink. And this is not a closed meeting, this is open for everyone. Do you have technologies that can support the needs of photonics in AI? You're welcome to join and voice it. And thanks to these generous sponsors, your participation in this online meeting is free. And now let me give the floor to John Pugh, Director of PIC and Quantum at Optica. John, take it away.
Good morning, afternoon, evening, wherever you are in the world. So as AI workloads scale and bandwidth demands continue to surge within hyperscale data centers, we find ourselves at that critical inflection point. Pluggable optics have powered incredible progress so far, evolving from 100G to 400G and beyond to 600G, where we saw prototypes at OFC 2025, which, according to Andy Bechtolsheim in an interview with Jose, should be in production in a year with a very fast ramp to shipments. The questions now arise: how long can this model hold? What are the limits of power, density, and thermal constraints? And when do co-packaged optics become not just an option, but a necessity? We're joined by experts shaping the future of optical I/O, and we look forward to a rich conversation on where the industry stands and where it must go next. As Jose said, thank you so much to all the sponsors of this meeting. Free access to the meeting would not be possible without you. So thank you to New Photonics, OpenLight, OptiWave, VPI Photonics, Fintech, Quantify Photonics, Axelink, PIC Advanced, Vanguard Automation, Nanoscribe, and ANSYS. Much appreciated. So as Jose says, we have integrators and many enablers in the room who are all looking for partners. So this meeting is not a webinar, it's a place to do business. So let's, all interact and see if we can do that today. So we've really been excited to bring together this roadmap of online industry meetings this year. You see, today we have co-packaged and pluggable optics. In a week's time, we have robotics before a bit of a summer break, and we return to medical imaging, QKD, new space, photonic-enabled AI, and all those on the right-hand side of the screen. So if you're not an Optica corporate member yet, please join us. Please contact us, any of us, and we'll explain to you the benefits. The main one, of course, is the global trusted network. We can introduce you to potential partners, customers, suppliers, investors, and even talent. We have the largest number of market reports, over 100 that are downloadable for all our members. We have year-round events, including these online industry meetings, in-person summits. As I said, the Agri-Photonics Summit is going on in the room next to me here in Fargo, North Dakota. We offer substantial discounts on many things, including exhibiting at our events and attending. We're able to promote your achievements as companies. We can record interviews and tell your story as a company. Storytelling is incredibly important. So get in touch with us if you would like to help in promoting your achievements. And of course,
on this call.
engagement is really important. So to download all of this content, scan this QR code. You can find the market reports, presentations, videos, tutorials, roadmaps, and much, much more. So we're also live on YouTube. So welcome all the YouTubers of the world. So if you have questions in YouTube, please type them in the chat and we'll voice them to the panel. In the Zoom, please do ask your questions in the chat. This is, again, not a webinar, so we will voice your questions. You can unmute and ask your questions to the panel yourself. So without further ado, let's begin. We're thrilled to welcome Fatini Karanu, Principal Hardware Architect at Optical Technologies at Azure Hardware Systems and Infrastructure. Fatini brings a wealth of experience in integrating optics with AI hardware, enhancing processing speeds and efficiency in data-intensive tasks. Fatini, tell us what we'll all be discussing at the PEC Summit in 2025 in Sunnyvale. The floor and the attention of everyone is yours.
Thank you so much, John. It's really a great pleasure to be here. Thank you for the kind invitation. I hope you can all hear me well and you can see also the slides on the screen. Give it a try. So I hope you can see the first slide now.
We can.
Yeah, perfect. So yes, thank you so much, John. It's a great pleasure to be here. Thank you for inviting me. I'm Fatini Karanu. I'm part of the Optical Technology Pathfinding team under Microsoft's Azure Hardware Systems and Infrastructure Organization. And the focus really of my team and the focus also of this talk would be the scale-up domain. So we're focusing on the scale-up domain and how we solve some of the interconnect challenges as we build AI systems. So before going into deeper into the presentation, just I want to give a brief of an overview of some big innovations coming out of the organization. So I'm very proud to be representing today here a brilliant set of teams innovating across the whole stack. Okay, so here are some innovations from silicon to systems. I think it goes without saying that a lot of code design and system optimization needs to happen in order to build and deploy AI infrastructure at scale under constraints of power and energy and cost, right? So really reimagining the traditional paradigm is needed. And this is what we do in the organization, innovating from cooling systems to platforms to servers, and more notably, even innovating and building our own AI accelerators, our Azure Magia accelerators you can see in the picture. So yes, I will focus on the scale-up interconnects and pods, and mainly talk about the scale-up domain, right? So in the thinking about how AI clusters are built, we can see here there are several pods, each one consisting of accelerators interconnected through a scale-up network. And the scale-up network really is the highest bandwidth, lowest latency network in the architecture. It interconnects multiple accelerators with each other inside the pod via probably one tier of switches. This is quite symmetric topology, so it's easy to write software on top, quite user-friendly in terms of software, but also guarantees uniform latency. And also this rich connectivity enables quite high reliability, as now communication patterns are really invariant to failures either in the switch or the accelerator side. So what I want to point out here is that up to now, copper is used in these connections, as you can see here, the brown ones within the rack in order to build pods, right? So pods are constrained in one rack, and that's the same goes for the inference workloads as well. So going forward, as we see the model size increasing constantly, and also the accelerator bandwidth also follows this trend, at the same time, we are not able to pack more and more accelerators and GPUs in the one rack, just because we're limited as to the power that we provision the rows and the racks, right? So this really is like a perfect storm, or also a perfect opportunity to start thinking about how we bring optics inside the scale-up domain to solve some of these challenges. So again, copper has allowed us to build single rack pods, and I hope you can follow me now on the slide number 4, John.
Yes.
Perfect.
Thank you.
Going from the left, as a baseline, using copper, we were able to build low cost, low power, and really high reliable pods up to now. However, the limited reach and also the power constraints that come with trying to extending the reach of copper by the use of retimers really push us towards the right? So the first thing we want to enable is being able to use optics in order to build multi-rack pods and solve this first challenge of reach inside the data center. And here, of course, introducing a new technology like optics in such a sensitive segment of the network, which is scale up in terms of cost, but also reliability, comes with some overheads, right? So here, a necessary step might be to try to deploy optics as a first step when needed selectively, so as to mitigate these overheads in terms of cost and reliability. However, even if we kind of try to solve this first challenge of reach with optics, still the increasing bandwidth and the power density inside the rack really pushes to where we eventually want to be on the right-hand side, right? We need we need to really leverage and unlock the full potential of optics, and not only be able to build multi-rack pods, but also those optics to be really better in terms of KPIs and a lot of different other aspects compared to copper, like bandwidth density, power, and BER. And it is there then really when the performance, cost, and reliability improvements will need to be satisfied, and that will depend on these on the best optical technologies that we can employ in this domain. So where are these trends really motivated from? These are really motivated from the accelerator side. So we need to think about how the future accelerator would look like, right? And what would be those future connectivity requirements. So in this slide, we list some of the main more important KPIs. Of course, there are more. For example, reach, bandwidth, latency, bandwidth density, energy efficiency, BER. And you kind of can see that the two different type of interfaces. It's the scale-up communication and off-package memory that might be needed in future in terms of workloads needed more and more memory, and so we need to extend beyond HBM, right? So the scale-up communication really sets the limits in terms of requirements, or let's say the target in terms of requirements, in terms of reach. Reach is not something we can compromise on, and this is really dictated by the scale-up communication, which means accelerator to accelerator, and either directly or through switches. Also, bandwidth density and energy efficiency are also dictated by these requirements, while latency and BER really are governed by memory interface requirements. So we really end up with a combined set of requirements at the end of this table, in which every solution and the scale-up domain really will need to kind of fit in. So if we take a look now, if we pick some of the favorite KPIs, let's say energy per bit and bandwidth density, and we can focus on this diagram, where we have been working really hard as an industry is in the lower right-hand side box, right, where we have developed technologies, we see proof points of technologies like co-packaged optics in this area, where actually what we're trying to achieve is like really being better than a traditional pluggable, right? Now, as we observe these trends, especially as we focus on the scale-up domain, where we really need to be going is the coordinate in the left upper side, where not only we need optics to be better in terms of energy and bandwidth density, but also there's a strong incumbent copper, which we need to kind of think around how we build optics in that realm, and how develop the technology, but also how we really deploy, how we define really deployment at scale for those scale-up optimized optics. So to conclude, going through the potential scale-up interconnect evolution, trying to list here some technologies that could be under consideration, starting from the left-hand side, technologies based on copper. As a first step, technologies like co-packaged copper and high-density pluggables and OBO might be a natural first step in order to introduce such optics in the scale-up domain. While as we move towards the second step in enabling the full potential of optics, this is where co-packaged optics with tighter integration, eliminating the power-hungry service and making use of more efficient die-to-die interfaces, wide parallel approaches, that could be really something that would be enabling technology for this segment. Of course, we need to come up as an industry with a kind of a framework, build proof of concepts, not only from a chiplet or a module perspective, but also from a system perspective, and really try to redefine how the deployment looks and to solve the cost and reliability challenges of optics at scale. So with that, thank you so much for your attention, and looking forward to the next speakers.
Great. Thank you so much, Fatini. Thank you for battling through the Zoom issues as well. So can I ask you what collaborations or open standards are most important for Microsoft in shaping the future of this optical interconnect ecosystem? Are you able to say what collaborations you have at the moment, or what collaborations you might be looking for?
Yeah, I think what I would say is that we really want to look through a variety of technologies that have the potential to fall in this left upper quadrant. And there are quite a few, right, in the industry. What we really want to do is to engage with the different technology developers and define how, as I said, a system POC would look like. What are these challenges that we need to solve from a system perspective? And how we deploy, how we service and make this reliable in order to really be able to choose or select some of those technologies and use them in the right application scenario, right? So I think this is the kind of engagement that we will be looking for.
Great. And how does Microsoft as a company assess when exactly to move from pluggable optics and to adopt these technologies live, I guess, is the question.
Yeah, that's a very good question. I think it's a quite complex exercise, and really goes through being really up to date and have really a lot of discussions across very many different organizations. As I said in my first slide, platform systems, the infrastructure, everything really needs to come together and to understand where is the right intercept for every kind of form factor or technology. I think from a technology perspective, I think it really comes also down to the readiness, right? The readiness is really important. So it's really important as to what is ready and what can be deployed and tested, and to really make us comfortable with deploying and introducing this type of new technologies in the data center. So yeah, making this first step, I think it's quite important.
Great. Thank you so much, Fatini. So I'm very happy now to introduce the second keynote of the session. So it's a combined talk between Chris Vissner, Vice President of Sales and Marketing at Avicenna, who offer a unique perspective with their disruptive technology, the modular light bundle optical interconnect platform. And this boasts high I/O density and energy efficiency of less than 1 picojoule per bit, addressing the specific needs of large GPU clusters in future scale-up networks. Also speaking in this combined slot is Dominique Schulten, Senior Director of Osram Opto Semiconductors, a global leader in advanced light sources. He'll share insights into Osram's 2D micro-LED arrays, a key enabler for Avicenna's light bundle platform. And these arrays offer exceptional brightness, pixel-level control, and scalability, forming the optical engine behind next-generation chip-to-chip interconnects. Chris and Dominique, the floor and attention of everyone is yours to showcase this incredible collaboration, something we love at Optica, of course. So please share your slides.
Thank you, Dominic, and good morning, good afternoon, everyone. Let's see how we do with our sharing exercise here.
Yes.
Okay, so just following on to what Fatini was laying out for us here, our focus with our micro-LED based interconnects. And for those who don't track us every day, we're a privately held company in the heart of Silicon Valley here in Sunnyvale. We're pushing now 100 people. We've been at this for the last 5 years. And we're squarely focused on the scale-up portion of the network, because LEDs do a lot of wonderful things, as I'll lay out in the next few minutes, but they are they are limited in reach. It's basically dispersion that limits the reach in a highly multi-mode interconnect technology. We will then, the second part will be presented by Dominique. We have an exclusive relationship on the LED side with Osram, the #2 LED company in the world, actually #1 in several of the sub-segments, and Dominique will walk us through that. But without further ado, I'm gonna fast forward to the next slide. I don't know how many people were at OFC, and in particular, how many people were at the workshop on Sunday that was hosted by NVIDIA, Trey Greer, one of the principal engineers from NVIDIA in particular. And he basically laid out a short list of specs, target specs. They are very similar to what Fotini presented. You see them here on the left. Energy efficiency is high on everyone's list. Shoreline density, he was a little lower than what Fotini just presented. Of course, these are all moving targets. Reach as well, a little shorter. He said 10 meters. I think Fotini just showed us up to 20 meters would be desirable. Reliability of 10 fit, that is about an order of magnitude better than existing pluggable transceivers, which are in the range of 100 to 150 fit failure in times. And he also laid out the cost target. Now that's to be hit by 2030 in their minds, and that's about 10 cents a gig. That is where copper is about today, so that is a tough target. We know that optical interconnects today are typically in the range of 50 cents to about $1 per gig, depending on what exact technology we're looking at. So what I just wanted to flash up here is how the LED technology that we're working on stacks up to this. We call it the light bundle. So if you see that term, that's basically our technology. We can hit today, we've already shown around the picojoule per bit because this is NRZ format, so this is very simple. The energy efficiency refers to everything from the driver to the LED to the PD on the other side, and then TIA and limiting amp. It does not include the additional typically SerDes that are pointing to the outside to interface to the electrical interfaces. Shoreline density, we're right around the terabit per millimeter today. This, what helps is it's a 2D array, as you'll see in a moment. Reach, we can do 10 meters. We can go a little beyond that. It's partially an energy trade-off. You can drive it harder. You can do also some dispersion compensation if you want that. I would say this is definitely extendable to 20 meters. It's never going to be a kilometer. Reliability, well, in order to get reliable fit rates, obviously we need to deploy a large number of these units, which hasn't happened yet, so we're pre-deployment, but we're off to a good start with the gallium nitride LEDs. They're very reliable. They are much less temperature sensitive. That's why the lighting industry has basically been taken over by LEDs in the last 5 years. And they're also very cost effective because we can leverage existing technologies, both on the transmit side with micro LED display technology for transfers, as well as on the PD side. For those who missed it, we just announced a partnership with TSMC where they're going to adopt the CMOS image sensor process to our high-speed detectors. That is something that's in all the camera sensors, and there are millions of those produced every month. So basically here is what the architecture looks like. I'm going to bring both up here. You have a substrate on which you have basically 3 chips. You have a transmit chip. These are all CMOS chips. That's typically in a 12 nanometer process node where you have your LEDs that are coupled via it's a little hard to see here, but there are little lens arrays that couple this into a fiber bundle that then carries it across, brings it out, couples it through another lens array onto a PD array. So those are 2 N12 chips. And then there is a high-speed SerDes for energy efficiency. The high-speed SerDes is typically in the kind of N7 to N3 process. Heatsink might be needed because the most energy is actually burned in the high-speed SerDes, but as long as we are in an environment where you have 200 gig per lane, that is just a necessary approach. You can then build this into an onboard optics module. That's actually the first focus, stay outside the package of an accelerator or a switch. Longer term view is you bring it inside the package once it's proven and deployed, and then you can go to much larger CPO modules. There is a lot of talk now about the kind of 12.8 to 14.4 tera generation. This is a slightly different way of representing energy efficiency and bandwidth density from what Microsoft has presented to us. It is a view that originally came from DARPA. It's again, you have the reach across the bottom here. Here is 1 meter in the middle. On the y-axis, you have a figure of merit that consists of bandwidth density and energy efficiency. So the higher the figure of merit, the better. It means the denser the interconnect and the more efficient it is. Just to level set everyone here at this middle line, the red line at the figure of merit of 1,000, that would correspond to a link that has a 1 picojoule per bit energy efficiency at 1 terabit per millimeter bandwidth density or shoreline density. So that's sort of table stakes. And what you see is, not surprisingly, for very short reaches, so a millimeter would be right here, copper today still does it very well. And when you look at cost and just how many of these interconnects are deployed, that's not going to get displaced here. Here's an HBM interface over 1 millimeter, very efficient. What LEDs do, so LEDs is this block here in the middle, they can just about take that efficiency and extend it from a millimeter to about 10 meters. That's what we're showing here. As you're going to longer reaches, not surprisingly, optics starts to dominate, and eventually single mode optics starts to dominate, which you have here represented by Silicon Photonics, and that of course extends way beyond the kilometer. An interesting new technology or a new application for an existing technology, rather, I should say, is VCSEL, and especially next generation VCSELs, especially next generation VCSEL arrays. This technology has received quite a boost from the camera image recognition sensors that we all find in our smartphones these days. But again, display or image recognition, those are slow modulation rates. So the challenge here is to bring those modulation rates up to much higher speeds. Then what do we do with this? So a timeline. I saw Microsoft was a bit more generic in their timelines. Obviously, everyone would like this sooner rather than later, but realistically, it's going to take, as Fontini said, it's going to take a moment to make that transition from a copper-dominated world in scale up to an optically dominated world. We just taped out and will receive back our second demo kit that will allow us to do something on the order of a terabit, call it 4 flows of 224 gig. That's coming later this summer. Out of that, we envision a first product to be what some people refer to as onboard optics. So this is still onboard optics on the PCB outside the package of an accelerator or a switch. But the same technology can also be packaged into an active optical cable. That, of course, has many, many applications, and that's an excellent way to prove out the technology because it can be deployed in a large number of configurations. And then fast forward, that's more at 2027 going into 28 timeframe when people are looking at these new optical high-density pluggable approaches. There's a big effort in the OIF. There are other efforts in the works. So that is definitely something that's coming. 12.8 to 14.4 tera is sort of the bandwidth that is expected to be needed coming out of an accelerator in about 2 years. Today, for instance, the NVIDIA Blackwells, they're at 7.2 tera. This is 7.2 tera bidirectional. Other accelerators are on the order of 6.4 tera. With this, I'm going to hand over to my partner here, Dominique at Osram, and he's going to give us a quick overview of what Osram is doing in this whole ecosystem.
Yeah, thanks, Chris, for the introduction already and what we do together, and also thanks to the Optica team for having me and us as AMS Osram. So yeah, I'm a senior director in business development in what we call micro emitters as a product line within the AMS Osram organization. AMS Osram is a publicly listed company, a global leader in light and sensor solutions. So I just give you a little background here because the overall message we want to provide here is that we are Avicenna's partner in enabling this in mass production, basically, what Avicenna is doing. So we are number 2 in LEDs globally by TrendForce from last year, and we are the global number 1 in automotive products. So what we do is we do emitters and sensors from LEDs to micro LEDs to lasers, biosensors like for vital sign monitoring, even image sensors, and whole optical modules. We have a workforce of 20,000 people in our back with 5,000 engineers. And last year, we finished our fiscal year with 3.5 billion euro. We are, as you see in euro, we are from the south of Germany. Our headquarters is in Munich. On the next page, I want to move you through what we do together with Avicenna and why Avicenna also choose to work with us. So, Chris, if you like to move on. So where are we coming from and why are we working together with Avicenna? So on the top left, you see that we have more than 10 years experience in micro LEDs. We started here on AR and VR and wearable devices in the past. We also launched last year, on 2023 actually, the first micro LED emitter in a car. So here, which you see on the second picture on the left. So if you buy a Volkswagen today, you might find our LEDs in the top headlamps. And this is actually very special because it's not only automotive qualified, or speaking about the quality part of it, also for transceivers, obviously, but it also comes with an integrated driver IC underneath. And then on the bottom, you also see that in terms of operations and manufacturability, we are on the edge of the industry with the first 8-inch micro LED facility, providing us a low particle production, which is more and more important when you talk about the small emitter sizes we are doing here together with Avicenna. So now on the right, you see what we actually do today, and that is the discrete micro LEDs. That is the number 1 here on the slide. This is what we do for displays, for example, for red, green, and blue LEDs. Individual LEDs, which we then basically print on a substrate or backplane for displays, or in the case of Avicenna, also on for transceivers. Number 2 is a monolithic array. This is a much smaller pitched device where the discrete micro LEDs in the top can go down to like bigger than 5 microns in a size of an LED. The monolithic micro LEDs can even go down to 1 microns. So there's potential to even go smaller going forward if the optics folks can follow us in terms of fiber sizes. And for number 3, what we also do is the assembly process. Here we do wafer-to-wafer bonding, chip-to-wafer, chip-to-chip. This really depends on the individual solution we need to provide. And the exciting part is what you see here down is in the images. This is actual hardware we built together with Avicenna. So you see here our blue LEDs lighting up on the right lower image on an interposer, which Avicenna is using today. So yeah, we are very excited to work with Avicenna and to follow this path together. Well, thank you.
Thank you, Dominique. I'll stop sharing and
Right.
hand it back to John.
Great. Thank you both so much, Chris and Dominique. We have a question in the chat from Chris Maloney at VPI Photonics. Chris, would you like to unmute?
Yeah. I might have just gotten the answer on that last slide, but I was curious, Chris, for your micro LED solution, are there advantages for different types of like multiplexing solutions? I mentioned just multi-core fibers, but it does look like that is what is used in your solution. But I know it's a little bit different than lasers, where you can do wavelength division multiplexing, things like that. So I'm just curious about the
Yeah, it's a good
options.
question. We get that question quite often. And I mean, with enough, as I said, with enough time and money, almost anything is possible. LEDs come in three fundamental wavelengths, so you could technically theoretically do that. We keeping the last of the five line items in mind, which is the cost. We, in the first approach, plan to keep it simple. So basically, single wavelength, and then just so it's just spatial multiplexing. But nothing precludes us from eventually going down another path. But it's still, we're creating a whole ecosystem here. So in order to get a successful product out in a useful time frame, we're focusing for now on a single wavelength approach.
Thanks, Chris.
Great. And a second question from Hamid Eslampur. Hamid, would you like to unmute and ask your question?
Yes, hi. Yes, so yeah, basically the question is the bandwidth or the shoreline densities that are shown, they are referenced in various presentations. For example, one greater than 1 terabit per second per mm. Are these they refer to the optical domain, I assume, or is it the electrical?
Well, I mean, it is the physical dimension, and it is the beachfront density. How much bandwidth can you get off an accelerator or a switch chip per millimeter of shoreline of beachfront? So, of course, it is the optical density of the optical emitters or receptors is a key contributor here, but it also includes whatever other packaging is necessary. It doesn't do one any good if we can have a super dense optical emitter, but we need a massive silicon stiffener around the setup to actually practically manufacture it. So at the end of the day, it includes everything. It is the whole package. Does that make sense?
Yeah, I think if I understood you correctly, basically it applies to both electrical and optical. Just
Correct.
basically how you're busing, transporting the data with that kind of a shoreline density.
Yes, indeed.
Thank you.
Great. Thank you, Hamid. A quick one from me, Chris. How is the Avicenna, Osram, now TSMC collaboration structured to accelerate commercialization? Are you targeting module vendors, system builders, or even cloud providers directly?
Again, multiple business models are possible here. We're stepping. There's lots of options, and we're down selecting to the ones that we expect to give us the fastest introduction into market. So obviously, we're leveraging best in class, if I may say, with TSMC. I think it's the recognized leader on the IC foundry front. Osram is definitely the LED market is a little more fragmented, so Osram is best in class in several key segments there. What you also notice, we haven't disclosed partnerships yet on the third portion, that is the fiber connection. Lots going on there, but there is always room for more collaboration, because it is an ecosystem with the end customers like a Microsoft, like the hyperscalers, the system companies, the OEM companies, think traditional transceiver manufacturers, then the large manufacturers, both on the transmit and the receive side, and of course in the middle of fiber. So it's a complex ecosystem, and in order to be successful with launching a new technology as a small company, which we obviously are, we have to have the big brothers that are experts in their fields and have a massive presence already.
Great, thanks. And a final question in the chat is from Ian McKenzie of the European Space Agency. Ian, would you like to unmute and ask your question?
Yeah, I'm just curious, what is the bandwidth limit per LED channel in your solution?
There's another great question, which we get quite often. For those who keep track of us in our publications, we have published 14 gigabits per individual LED already. That came with a little bit of pre-distortion trickery, but we can definitely see how you can get to 16 gig. Maybe we can push this to 32 gig eventually. It has to do with the GaN material that acts different from indium phosphide. It's never going to be efficient to try and hit a 200 gig per lane approach like is common in the laser world. But it is not needed because the LEDs are much smaller. I mean, these are the current generation is 50 micron pitch of LEDs. So, but right now the highest data rate per individual LED we have shown is 14 gig. The first product we're launching will run at 4 gig per lane, so we're staying quite a bit away from the maximum. We're confident we'll push that, double that to 8 gig in the near future.
Thank you very much.
Great. Chris and Dominique, thank you so much. I'm going to move on now to, I'm pleased to welcome Doron Tal, Senior Vice President and General Manager, Optical Connectivity of New Photonics, and KF Tsai, Vice President at Centera Photonics. And this joint presentation brings together two key innovators addressing the limits of traditional pluggable optics and exploring practical paths towards scalable optical interconnects. New Photonics is developing novel pluggable transceiver architectures that push the boundaries of speed, density, and power efficiency. And Centera Photonics, a leading ODM and manufacturing partner, specializes in bringing advanced optical modules to volume production. Together, they're collaborating on next-generation pluggable solutions that bridge today's hyperscale demands with the emerging requirements of co-packaged optics, combining system-level insights with manufacturability and integration expertise. Doron and KF, the floor and the attention of everyone is yours. Thank you.
Hey, John. Thanks. Great to be here. Good morning, good afternoon. Can you hear me okay?
Yes, clear.
And see the slides?
Yes.
Okay, perfect. So great to be here. So New Photonics is a fabless semiconductor. We design, develop, and manufacture photonic integrated circuits for data center optical connectivity. Our focus is on enabling scalable module manufacturing through integration and simplification. We help our customer eliminate complex optical assembly steps like laser die attach and wire bonding, which directly improves the yield and accelerates the time to market. Our NPG PIC solution supports both DSP base and LPO pluggable transceivers at 800 and 1.6 terabit per second. They combine high level of integration, performance, and production readiness. And so when we look ahead for, we see the success of LPO as a critical stepping stone to CPO. We're now productizing high capacity, low latency, low power chiplets, addressing scale up and scale out CPO-based systems. So our solutions for pluggables really consist of two types of solutions. In this product family, we have an optical head transmitter on chip for DSP-based solutions for targeting 1.6 terabit per second optical transceivers. This is actually what our partners at Centera Photonics are working on and going to be sampling. We also have our NPG LPO PIC. This is a high performance optical front end. And as you know, in LPO solution, there's no DSP. What we go ahead and integrate on top of our existing solution, which is integrated lasers, modulators, we also integrate our optical signal processor, which is effectively operating as an optical equalizer. And in this application of LPO, basically, I think we're all familiar with the, let me put the laser pointer on. We're all familiar with the classical module. This is working very well and is now ramping up in the market. These are 1.6 terabit per second optical modules with DSP, laser, driver, PD, and these are working very well. These range from around 30 watts per module. I understand with the new advanced DSPs that may actually be more like 25 to 30, but it's still quite a chunk of power. Industries productizing LRO modules where only the transmit side DSPs place. This is certainly saving some power, saving some cost. And then the first generation of LPOs, what has happened there is it reduced power a lot. However, there are some interoperability issues with LPOs as non-retime traces introduce more insertion loss in different types of scenarios. What we are introducing with our NPG 102 family is an integrated optical signal processor integrated within the optical head. So effectively, we are correcting for electrical side impairments, but processing them in the optical domain. So kind of like to visualize that more as data rates scale to 200 gig per lane and even 400 gig per lane. RF, the PCB design faces severe signal integrity challenges due to increased insertion loss over non-retimed trace segments in the LPO application. With the electrical domain equalization becoming increasingly bandwidth limited, optical domain equalization provides a complementary path to restoring signal integrity and ensuring reliable interoperability across every slot in the rack. So basically, we're offering TDEC BER and extension ratio performance boosts with our optical signal processing. And as we look at CPO coming of age and per lane speeds increasing, we're looking at how we're integrating this optical signal processing in our CPO chiplets. And it's really becoming a fundamental proof point for high speed, high bandwidth optical processing. So I'm not sure if we have KF here or CT on the line. They've been very good partners with us. They're going to be sampling the 1.6 terabit per second transceiver, OSFP transceivers to their hyperscaler partners this second half of this year. They're excited about the LPO projects coming of age as we're starting to see also RFPs in this domain. So very excited. I'm not sure if KF is on, wants to chime in at all. I haven't checked.
Yeah. Okay, well, amazing progress. Thank you, Doron. The LPO project is amazing. So you shock people every year at OFC with your demonstrations. Yosef Ben Ezra told us at OFC 2026 we should expect more than 6 terabits per second per square millimeter on a new photonics co-packaged module by next OFC. But we're about 3 months on from when that interview with Jose was done. Are we still on target with this?
Yeah, we're on target for that. That's our CPO solutions that we will showcase at OFC. Where right now we're planning for ECOC. That's the next major hard milestone. We're also going to have a very exciting product announcement over there in optical signal processing. All these technologies that are now becoming of age on the module are clearly going to migrate themselves onto the CPO chiplets and add value there as we increase integration and be able to process some of the electrical impairments much closer to the GPU, TPU, XPU.
Great. Thank you so much, Doron. I look forward to the announcements and the demonstrations at ECOC. So in the interest of time, let's move to the next speakers. So with all the development we see in pluggable and co-packaged solutions comes the rigorous efforts behind the scenes of device and system simulation. I'm now very happy to welcome 3 Optica corporate members who are also sponsors of this meeting to showcase briefly their offerings that underpin the success of these devices and systems. So firstly, Ahmad Attia, please share your slide and tell us about OptiWave.
Sure. Thanks, John. And hello, everyone. So at OptiWave, we offer different software packages to simulate devices and systems, as well as instrumentation. So we offer component level devices using software like it's called BPM, beam propagation method, fiber, mode, where you can design multi-core fibers with photonic crystal fiber, hollow-core fibers, as well as finite difference time domain software, which can design devices with it, and then integrating software. We have instrumentation software, which enables you to automate setups to characterize devices or systems. You can talk remotely with any instrument. It's not dedicated to a vendor, and you can do it remotely. And the system level software, which is mainly can be related to this talk today, is we have a comprehensive software which you can simulate different system levels. Like here, for example, we show a PAM4 224 gigabit per second system, 112 gigabaud. We added up a new component in the system, which we just heard about the pre-emphasis and the pre-distortion equalization. So in this system, for example, if you use a filter here, the system filter with 50 gigahertz, you can see that how's the eye is closure, but when you introduce the digital pre-emphasis component, you can open up the eye and then you can control the filter characteristics as required. The filter can be in analog domain or in digital domain, so you can digitize it and then you can control the quantization levels, the number of tabs, and so on. The other thing is about our software capability is you can integrate it with other software packages, which I mentioned to you, as well as you can integrate it with MATLAB software, Python, and photonic integrated circuit devices like Lucida, so through EPCAS software. We also introduce a machine learning part of the software, which you can train the system, you can generate control and second layer of management of the system through the algorithms for machine learning. So with this, I'm open for any question if there is any. Thank you.
Great. Thank you so much, Ahmad. Secondly, I'm going to welcome back Chris Maloney to the meeting. Please share your slide and tell us about VPI Photonics.
Yeah, thanks, John. At the top of the meeting, I think you mentioned Silicon Photonics is at an inflection point. I couldn't agree more. And with that, one of the challenges comes in with the design, when you're actually designing a photonic integrated circuit for full system level performance. And that's what we really focus on. So for example, you have a PIC designer, maybe they're designing a micro ring modulator, they're off in their own world doing that, and then they end up with a model. Okay, what do they do with it? And in the end, it needs to be used by the optical systems team, right? So what we provide is in a single user interface, the ability to design and optimize your photonic integrated circuit for full system level performance. So in the lower right corner, you can see an example of a schematic 800G WDM PAM4 link. This is representative of the optical networking switch architecture that NVIDIA proposed. And so this example is already in the software. It's a good starting point. If you kind of walk through the schematic, there's 8 channels, so 8 lasers, an array of 8 micro-ring modulators. The signal passes through a fiber with all the nonlinearities associated with it. And then there's a receiver, and we include things like feed-forward equalization or DSP or whatever. So what we do is we bring those two tools together in one seamless interface with this hierarchical design flow. And if you want to take that to the next level, as optics and electronics get closer and closer together with these co-packaged optics solutions, there'll be some interactions between the optical and electrical domains. And so we actually partner with Keysight, and that schematic that I just showed you can be called directly from Keysight ADS. And so for full electrical optical co-design, And so the parameters from your VPI schematic can be available to you within Keysight ADS workflows. You can run sweeps on all the optical parameters and optimizations. So we're really trying to address this next inflection point where optics and electronics are being used together closer and closer inside of the data center. So with that, I have my email there in the lower right corner. If anyone wants to reach out to me, feel free. We offer demos, evaluations. But yeah, thanks, John.
Amazing. Thank you, Chris. And thank you, VPI Photonics. So thirdly, I'd like to introduce Shin-Sung Kim. Please share your slide and tell us about ANSYS's developments on simulating co-packaged solutions.
Okay. Can you see my screen?
Yes, I can. Thank you, Shin-Sung.
How can I remove this?
Sorry?
This one. How can I remove this one? Okay. Okay. So this is an overview of the solutions we have been developing in ANSYS in support of CPO, and many of these are applicable to pluggable optics. So leveraging the ANSYS multiphysics portfolio, we can address various challenges that we are facing from the CPO, which is typically made of, as you can see in the center, ASIC and silicon interposer with PIC on the substrate, and again, EIC, laser, and optical I/O interconnect on the interposer. So regardless of the type of stacking you use, the challenge you face are very similar. So first, photonic integrated circuit is a big piece of CPO design. We have numerical tools for simulating at component as well as circuit system level. To get the light in and out of the chip, we use surface gratings or edge couplers. The coupler design requires multi-scale simulations involving wavelength scale structures and much larger scale micro lenses. We provide an efficient workflow using numerical and GMAX Optics Studio to address the challenge. Thirdly, the performance of PIC can be affected by temperature. We have tools like IcePack and Redog SCET for thermal management by importing thermal temperature map into PIC simulations and assessing the temperature-dependent performance. Next, the metal tracks, for example, in the electro-optic modulators can affect the integrity of electrical and optical signals. We can use Raptor X or HFSS to extract the S parameter for different metal connections. For power integrity and reliability, we have a Totem and Redog SC that allows electron migration and voltage drop simulations. We also have a tool for electrostatic analysis. Lastly, structural integrity can be simulated with a mechanical and Redog SCET. I have attached some other slides, but these can be accessed from the optical library. If you have interest, reach out to me and we can start our discussion. Thank you.
Great. Thank you so much. Optiwave, VPI Photonics, and ANSYS. As someone who's not only used these softwares, but also taught with them in my previous career, I can't tell you how important these are for the future of these, co-packaged optic solutions. So I'd like to now shift the meeting a little to the crucial platforms for integration of different materials. So I'm pleased to introduce Joshua Shaler of Heteromerge. Hopefully I said that correctly, Joshua. A company pioneering hybrid photonic integration through advanced microassembly and packaging techniques. Today, he'll share how Heteromerge's modular integration approach is enabling more flexible, scalable, and cost-effective assembly for both pluggable and co-packaged optics, bridging the gap between cutting-edge PIC designs and real-world manufacturability. Joshua, please take it away. The floor and attention of everyone is yours.
Thank you, John. You did well on the name. Thank you all also for participating. Is my slide visible?
Yes, it is. Thank you.
Perfect. Okay. So let me introduce ourselves. We are Heteromerge, a German-based startup, and we offer enhancement upgrade to photon lithography systems. I know some of the following speakers, or at least I hope so, will go into detail about this technology. So let me maybe just briefly say that we are printing mostly on the micrometer scale here, often with optical grade polymer materials, though glass ceramics are also possible. We as Heteromerge, we offer a multi-material printhead for these systems, which means you can print objects out of up to 4 materials by exchanging the materials during printing if you want over and over. Here you can see such an example exchange in an open printer. Let me see. Doesn't seem. Oh, okay. Now I hope the advancements is okay. So what our system does for our customers is to realize their multi-material prints with an automated and fast, reliable material exchange. It also offers unprecedented precision for multi-material printing down to low nanometer scale accuracy. That allows for small and precise, reliable optics printed all in one. Whether you need optics with chromatic correction, you need apertures printed alongside spacers, flexible parts, or any other material-dependent features. Lastly, our upgrade to 2PP printers retains all the advantages of these systems, which, for example, the substrate independence of 2PP systems. Which in effect means you can print directly on chips, on VCSELs, on fiber optics, whatever you want. Here I brought you some examples of print objects we did or our esteemed customers did. Some chromatic corrected optics, some optics with aperture materials, laterally printed optics here, or optics with air gaps and spaces. So what concretely does Heteromerge offer? So first of all, for customers who have 2PP systems, we offer our hardware as system upgrades. We also offer materials, and for people not owning a 2PP system, or for those maybe hesitant about the upgrade, we offer feasibility studies and printing services. Lastly, let me quickly mention that if you want to see the system in action or want to discuss more micro-optics with us, feel invited for next Wednesday when our second webinar starts. Thanks for the attention.
Great. Thank you so much, Joshua, for introducing us to the company and what you do. So following the insights into the high-precision hybrid integration of Heteromerge, where we now turn to Rolando Farini, Chief Product Officer at Femtoprint. Rolando brings a great perspective on enabling true 3D microfabrication within glass using femtosecond laser technology. At Femtoprint, his team is pioneering new pathways for integrated photonics by fabricating complex optical components and packaging structures directly inside substrates, pushing the boundaries of miniaturization, customization, and optical functionality. Rolando, please take it away. The floor and the attention of everyone is yours.
Thank you, John. I think you see my slides.
Yes, we do. Thank you.
Perfect. Thank you for the kind introduction, and hello, everybody. Thanks for the opportunity of spending the next couple of minutes introducing you to the product offer of Femtoprint in terms of glass microcomponents for fiber connectivity, specifically for co-package and pluggable optics. So first of all, a couple of words about Femtoprint. For those who don't know Femtoprint, we are an Enosemi in Switzerland, specialized in laser micromachining of glass microcomponents. Where, let's say, in spite of the name, we don't do printing, so we don't add material, but we remove material with a combination of laser writing and material processing. And with this technology, we can produce glass microcomponents for several markets and applications, going from medical to what we are telling today, so to co-packaged optics. We are 40 people, mainly located in the headquarters in the south part of Switzerland. We have a site in the west part of Switzerland and also one colleague in the US. So today I'm telling you about fiber-to-chip connectivity and what Fentoprint can do, going hand-in-hand with the customers from the engineering phases, from feasibility and prototyping up to pilot and volume production. When I say volume, it is volumes compatible with what is required today for co-packaged optics and optical transceivers, because we can produce actually already at wafer scale. And what we produce are components, glass components for packaging and assemblies of specifically PICs, thought for fiber-to-chip connectivity. We provide the following functionalities: high precision fiber alignment, beam routing, and beam shaping. To be more precise, typical glass components are like the one that is depicted here, which is simply a mock-up that is combining, for example, a micromirror, waveguides, and inlets for fibers. So all our components are always combining more than one functionality. Among these three pillars, what we can provide are very high precision V-grooves or 1D or 2D hole arrays for high precision fiber positioning. High precision means tolerances in the order of plus minus half a micron. We can provide glass waveguides, but also spot size converters, fan in, fan out in 3 dimensions, single mode, multi-mode, also directional couplers. And we can also provide beam shaping elements like micromirrors, which are very much used today to make the light turning at 90 degrees or almost 90 degrees in very miniaturized components, or also micro lenses. And for both waveguides and micro optics, we can also offer today a new service which is called Design for Manufacturing, where we can help customers designing components that are already manufacturable, which is speeding up the engineering phase and also reducing the cost of the development phase. So the components we provide are always combining, as I said, several functionalities with a relative positioning of plus minus 1 micron in a monolithic integrated manner. And we go from design up to the volume production. And with this, I'm done, and I'm here to answer questions, if any.
Great, thank you so much, Rolando. Can I quickly ask, what partners you're looking for to move your efforts in co-packaged optics forward more quickly?
So we are looking for partners for adding up ancillary process steps that we don't have in-house, but that we need to speed up the deployment at wafer scale. We're talking about especially about coatings, about dicing, alternative dicing than our own dicing. Also, we are open to discuss with partners that are providing platforms for design that are also integrated AI functionalities. These are the types of partners we are looking for.
Great, thank you so much, Rolando. Let's move on to Matthias Lauermann, Head of R&D at Vanguard Automation. Matthias leads the creation of industrial solutions for photonic wire bonding and facet-attached microlenses, enabling high-precision, preform, 3D printed interconnects that simplify hybrid integration and scale to mass production. Vanguard's work is central to enabling high-volume, low-loss, co-packaged optic architectures that join disparate PICs and fiber arrays without traditional active alignment. Matthias, please take it away. The floor and the attention of everyone is yours.
So thank you, John, for the introduction. I hope you can see my slides and hear me well.
Yes,
okay.
Clearly.
So what we at Vanguard, what we are providing are industry solutions for photonic integration and packaging. To this end, we offer basically 2 machines. One, it's a 3D lithography machine. As already mentioned, we're also using 3D nanoprinting to provide optical connections between various optical elements. We also offer a post-processing solution, so bridging the complete production chain there. So how do we do this? We have basically 2 flavors of connections. One is the photonic wire bond, you see in down left. So here an example between multimode fibers or fiber to a PIC, which is basically a 3D printed optical waveguide. But we also offer facet-attached microlenses, which adapt the mode field or, for example, change the beam shape for relaxed alignment tolerances. So we're targeting, as mentioned, like an automated processing for the photonic integration. And this lends itself for example, active device integration, but also the wafer processing, as you can see here in this video, if it runs. So now in this video, you see a first step like for the pre-processing. This is a local dispensing of the optical photoresist, and this is done in our reprise 1000. And this is basically both machines can process a full wafer. So we have the capability to do wafer level processing. Here it goes into the wafer in our lithography system, where then the individual sites are processed and the coupling structures are written. At the end, we can also have here then a post-processing where the liquid photoresist is removed, here also on the complete wafer level by rinsing away the photoresist and blow dry, UV curing, all integrated. The structures we print, they offer a high reliability and yield, and the mode field matching for both either the photonic Wi-Fi bonds or the micro lenses, they allow for very relaxed pick and place tolerances. So towards industrial usage, we have also, together with our partners, several experiments. Of course, what is needed for industrial usage is high yield and reliability. So on a high yield, we have here on the left side a study where we looked in total around 260 photonic wire bonds between fiber of fiber as a test assembly or fiber to Silicon Photonics PIC. And there we have all like 100% yield below 2 dB. Towards the reliability, we do a test against Telcordia specs. For example, here a damp heat test of photonic wire bonds passing over 2000 hours, or together with our partners, high power operations of the micro lenses at elevated and room temperatures. Also with a partner like Sumitomo Electric, what they recently at OFC published is a out-of-plane coupling of, you see it in the top, with two lenses, fiber to the chip, which is especially targeting CPO connectivity there. And they also tested it for then further processing like reflow soldering, die bonding, which the structures passed. So in short, what we're offering is basically the complete turnkey solution for this processing and production of the optical elements interconnects.
Thank you, Matthias.
Thanks a lot.
Thank you very much, and really impressive advancements on the wafer scale processing that you're doing.
Thanks.
So I'll now introduce the final collaborative presentation between Jörg Smolensky, Business Development Manager at Nanoscribe, and Stefan Heinemann, Managing Director and VP Sales at Fix Photonics Assembly North America. Together, they'll explore how Nanoscribe's 3D microfabrication technology, combined with Fix's assembly capabilities, are enabling the next generation co-packaged optical modules. So let's highlight how the integration of additive micro-optics into mass production workflows deliver low-loss, alignment-free interconnects that are critical for future optical networking and AI-driven systems. Jörg, please share the slides. Jörg and Stefan, the floor and the attention of everyone is yours. Thank you.
Hello, everybody. Thanks for the invitation and the possibility to talk here. I will give a first introduction to our technology. Basically, that's what we can do to enable low-loss optical interconnects. So we are a company which is now around, let me quickly see. So we are more than nearly 15 years old. We are 100 people in Karlsruhe. Here you see a look into our lab where we have several systems for doing feasibility studies for our customers. And we build micro CD printers for industrial applications. And here the co-packaged optic is one possibility where we can enable very low lossless and better coupling. Since December last year, we are now part of the Lab 14 group. So what is the goal basically in photonic packaging and especially co-packaged optic is to combine electronic printed optical components to make it even more compact and less powerful power usage. So here's an example of a package prototype where you can see the large view with electrical and optical components, zoom in where you can see the PIC and the fiber attached, and then on the PIC you can see another zoom in where we basically are printing optical elements directly and precisely attached to the PIC to adapt the mode field to enable low losses. So we can print on any kind of optical material, silicon nitride, silicon on isolator, gallium arsenide. We can print on different components, photodiodes, fibers, VCSELs, classical way. We have a dedicated product portfolio for this and also patent portfolio. The question is now, where do we do this? Basically, we have always fibers in the optical elements, so we can enable the better coupling from the fiber sides. On the ship, the PIC chip, it's mostly on the edge, but what is coming more and more is also on the ship surface, so that's quite interesting. There's a question about shoreline density. If you go to the surface, then you don't have that issue anymore. So you see here some images, and I will go a little bit more in details quickly on this. So for this, we supply a full system and usage. We have a software where you can easily set up and very, very nicely define the optical elements you need, from aspherical lenses up to periscopes with polynomial surfaces. We have in-house possibilities to characterize them. As Matthias already mentioned, environmental tests are important. Also, we have done this with our resins, these thermoshock tests or these heat damp tests. This is for the fiber, basically. That was too quick. So here's some examples. One big difference we have is we have a couple of different resins. So you can see this here on the left side. So we can adapt a little bit the resins we require to the resolution, or even to the coupling enhancing the coupling efficiency, because you have a different refractive index. So that's very important for periscopes, for example, because you have a larger acceptance angle to better transfer the light from one side to the other. I will not go into the details. These are just keywords. Most of the people here in the audience know what they see here, so I don't think I need to explain this in details. On the edge of a ship, we print precisely to the edge, less than 100 nanometer precisely aligned, which is crucial. Every nanometer gives a little bit more of loss. We can have very high repeatability on the mode fields. This is, again, if you want to print on fibers or on chip, you need to have the coupling, and you have a good overlap of the two mode fields to enhance the transfer of the light. Losses are down to 0.8 dB, for example, depends on the material and the design. Again, some examples on the environmental tests our materials have passed and the designs have passed. The one thing which I really would like to stress, I think, is the vertical coupling. This is something, as mentioned, is getting more and more important. So you see here two examples, and then you can by yourself get creative. You see here one example of a polynomial prism mirror with a lens on the edge, which enables on the side vertical coupling for example, to a fiber or even to another ship. This in the lower image, you can see a tapered vertical coupler. So this is for quantum photonics and for single photon detector in quantum areas. Also, this is a possibility to enhance the loss, reduce the losses. This is working even at cryogenic temperatures. In total, as shown here, we can print on fibers, on gel packing tray. We can do single parts. We can do multiple parts, batches, or on wafer level. On wafer level, it really depends what you need there and what is the quantity in order to fulfill this. So we go up to 8-inch with our system. And it's mostly for this kind of application where it makes sense to all, in our opinion. So for the moment, that's basically showing what we can do. So we can do from prototyping for just very complex surface couplers. So that was on grating couplers, for example. We can do also other optics. So that's not in this area here in this audience. We can do microlens arrays, could be interesting in some applications. Then it can be done with nanoimprint, for example, with EVG, to go to millions per month, millions per weeks, to have a higher mass manufacturing capabilities. And clearly with the system, we can do direct manufacturing of several thousand pieces, depending on the market requirements. And we scale up with the market right now. Thanks for your attention. And I think Stefan is in the room. I hope he managed to get out of the audience with you, John, and he will give his part of the talk.
Yep, I'm here. Thank you so much. I just sent a request for sharing. Right. All right. I hope you can see my slides. Thank you for the opportunity.
And you're not yet in full screen mode, Stefan.
Thank you for the opportunity to talk here, and you may recognize some of the pictures that you just showed before. But anyway, I'm gonna talk about how we use lens printing for CPO applications, and our general expertise in the field of lens is in the field of optical interconnects between chips and from chips to fibers, and we do in high volumes the V-groove attachers that everybody knows of, the surface grading couplers, in an automated way, and we use spot source converters either based on ion exchange glass or silicon nitride for improving our coupling efficiencies. That only gets you that far, and applications in quantum and also in optical in the CPO world. That's for better and better coupling efficiencies, and that's where we deploy designing and printing of optics, as you can see it in the lower right, where we directly print lenses, beam shaping optics, beam deflecting optics on fiber arrays. That is used for connecting chips, but it's also used for wafer level probing. We talked about, or you saw those pictures on making two-dimensional lens arrays on top of chips. So this specific application is when shoreline density is not sufficient for connecting chips to chips. And the specific chip shown here is actually for free space optical communication. So if you look closer at the chip, at the image at the lower left, you see that we print a freeform optics. It's not homogeneously attached to the surface of a chip, but we print a free shape optics and then build up the proper optical structure in a two-dimensional array that combines shaping and deflection in one device on top of free chips for free space optical communication. You saw those images before from Europe, so there's no need for me to revisit that in detail. But one of the things that I wanted to elaborate on a little bit is the surface coupling efficiency with surface coupling from wafers, which is obviously a very versatile tool, often today made by surface gratings. Surface gratings have the big disadvantage of dispersion, and printing tapers in combination with deflectors and beam shaping elements allows you to do two-dimensional arrays at very low loss. And we heard the number of 0.8 dB for surface coupling. Another application of using this printing technology is actually like alignment features. So snap-in connections for fiber arrays, freestanding fiber arrays to chips. And the benefit here is, as you push again the coupling efficiency from fiber arrays to chip well below the 0.8, 0.5 dB mark, what you need to do is precisely align the fibers relative to the emitters and the PICs. And that's where just the manufacturing tolerances of fiber arrays and package PICs together are not compatible to reach that space anymore. Let me quickly introduce one slide to our base in the United States. We were just recently designated as a tech hub in smart photonic sensing, in analogy to the Elevate Quantum in Colorado, which is a 3-year program, and that's where we really push the technology of low loss, low cost optical interfaces. And now we're coming back to the technical part of the presentation, where we're using things like we were using rapid prototyping as a design and engineering tool in the value add chain of developing co-packaged optics. So the goal here for us in the United States as FIX is to expand our expertise in optical interfaces for lowest losses by proper mode matching, and we heard this before, free-form optics, but also fully understanding the assembly tolerances for pluggable interfaces as it's required for TPO. The big benefit that we see here, besides what we all saw before in today's meeting, is that this is lens printing is a very effective tool to evaluate or to put the experimental stake into the Monte Carlo analysis that go into those connectors. I want to conclude my presentation with just showing you the benefits of really what we get here from mechanical design, optical design, to verifying the performance in process and project timeframes of weeks and not months. And this will allow, and what you see here on the right side is just one of the early examples of edge emitting, edge coupling, pluggable interfaces. Thank you for your attention.
Great, Jürgen, Stefan, thank you so much for highlighting your collaborations there. Really impressive. So in the interest of time, as I realize we're already in a slight overrun, I'd like to move to the final crucial segment of this meeting, where we'll look at enabling the future of pluggables and co-packaged optics through test, assembly, and ecosystem integration. So this fairly rapid fire session features key players in the co-packaged optics value chain, each delivering a focused 2-minute presentation perspective on the tools, technologies, and strategies delivering scalable deployment. So firstly, Travis Scott from FineTech will spotlight precision alignment and bonding solutions, enabling high yield, high accuracy photonic assembly. Thank you, Travis. The floor and the attention of everyone is yours.
Hello, thank you very much. Can you hear me okay?
Yes, thank you.
All right. Yeah, so FineTech has a 30+ year history in optical and optical electrical package assembly. So we offer submicron die bonders from manual to fully automated with tailored equipment, stage designs, process development, as well as technical consultancy for advanced packaging in optics and optoelectronic applications. We bridge the gap from R&D products. We are just trying to get your kind of proof of concept off the ground all the way to fully automated production. We also support the ramping up at OSATs, CMS, and EMS facilities. We've got quite a wealth of experience going through that kind of difficult phase that a lot of customers reach. And focusing on co-packaged and pluggable optics, we've broken it down here into a very simple divide between laser, single photon emitter, and detector sources, where we address this with adhesive bonding, eutectic soldering, thermocompression, and thermal ultrasonic attach, as well as the optical electrical assembly. So this is things like lenses, filters, fiber attach, this kind of thing, which is mainly ultraviolet adhesives, as well as some other glues and solders. And like we stated, we bridge this gap all the way from the first R&D devices on tabletop systems through to fully automated production offshore or onshore at different OSATs. If you have, sorry, for some reason the slides, yeah. So if you have any questions or you'd like to follow up or go through this kind of technical consulting first stages, please feel free to get in touch, and we're happy to hear from you. And thank you again for Optica. You always have fantastic curated events, a fantastic learning opportunity, and great to attend. Thank you.
Thank you so much, Travis and FineTech, once again. We move straight on to Kees Propstra from Quantify Photonics, who brings a test and measurement lens, highlighting the evolving requirements for validating high-speed optical and electrical performance. Thank you, Kees. Please jump into presenter mode, and the floor and the attention of everyone is yours.
Yes, hello everybody. Hope you guys can hear me okay and see the slides. So thanks Optica and John for organizing this excellent webinar. Obviously, this is a great subject. We all have been working on this for a while. So before I get going, I wanted to show something about, you can see there's a little change in our logo. We're now Quantify Photonics, a Teradyne company. So we were acquired by Teradyne. As of June 1st, we are part of the company. So of course, it's a very exciting new chapter in photonic test and measurement. So, John, you also asked the question, what can Optica do for you? This is a great example of ecosystem partnerships to drive the industry and really accelerate the scaling of photonic IC. So what we believe is the synergy of combining a leading ATE company with the leader in photonic IC test obviously will really enable next generation solutions for high volume photonic IC ATE test. So we all know the problem statement. We need to do high volume manufacturing of optical wafer-based technologies. We've done it for the semiconductor industry. Now we need to do it for the optical industry. It is quite different. Obviously, we need to validate optical parameters. We have the complicated probing and fiber array attachment. And since it's kind of new, before you start deploying these technologies in the field, you really want to do 100% testing on the high-speed I/O interface. But the good thing is there are solutions. So what we're doing to enable this is, one, we'll have turnkey solutions to do more complicated measurements like complete wavelength polarization dependent loss, parameter scan for devices. We're working on new product ideas like high power lasers, ELSFP modules, lots of channels, lots of wavelengths to drive your device as part of the testing, or really high density, high channel count optical power meters. Think testing in parallel. Obviously, very important. The third point is, this is really the synergy of the acquisition. We need to replicate the traditional semiconductor industry by providing photonic IC ATE test solutions. So having an ATE company, photonics company, and a probing company, those solutions are really critical and going to drive the industry forward. And last but not least, since we need to do a lot of testing of the high-speed interface at speed, kind of 100% testing at speed, you need to have a different approach to that. So you need to have a paradigm shift. You can't use R&D boxes. So we have with our QCA, QCR series, we can do testing in parallel of multiple channels to really have an optimized test flow. So that's our company in a nutshell. If you guys have any questions, please reach out. Thank you.
Amazing. Thank you, Kees. Testing is such an important part of the industry, so not to be overlooked. So thank you. I'm going to next move on to Tiger Nenonime from Axelink, who offers insights from a major transceiver and optical module manufacturer, sharing perspectives on integration and volume deployment. Tiger, the floor and the attention of everyone is yours.
Right, thank you, John. So this is Tiger Nenonime with Axelink. So we are one of the manufacturers of the optical transceivers. Here in this slide, we have the product availability and also product soon to be available for 800 gig and 1.6T pluggable optics. We have all coverage from short reach with multi-mode, single mode, 2 kilometer, 10 kilometer, and beyond. And when it comes to 1.6T, we foresee coherent optics is also playing a role for LR, 10 kilometer optics. As you can see, I plotted a couple of graphs showing the power consumption and the power efficiency. LPO indeed providing you the best power reduction. However, you can see LRO also still providing the great power efficiency as well compared to DSP based. In the past OFC, we've demonstrated a couple of interesting products, immersion cooling compliant pluggable transceiver optics. You can see MPO connector plugged in. So this is very unique that you don't need to have a seating on the cabling output. At the same time, we can make sure the light pass doesn't get the obstacle by the liquid. On the right-hand side, we've done the ELSFP at the OIF booth. We demonstrated 23 dBm 8-channel ELSFP, but we are scaling up to much higher power bandwidth. We are also working on the NPO, CPO development. So I'm glad to see lots of technology enablers here, but we are always seeking for technology enablers for energy efficiency, manufacturing improvement, 448 compliant optics components, as well as higher fiber count coupling technologies as well. So that's pretty much all. Thank you very much.
Great. Thank you, Tiger. Amazing advancements. So I'm going to move on now to Antonio Teixeira from PIC Advanced, who will outline innovations in active alignment, packaging, and photonic chip design from a fabless PIC solution provider. Antonio, if you'd like to share your slides, hopefully the floor and the attention of everyone is yours. Thank you, Antonio, for joining.
Hello, everyone. Thank you for invitation, and let's go through because the time is precious. So let me see. Okay, so we are just a quick look. PIC Advanced is a small company that was born in Portugal, now has headquarters in Portugal, and now has some branches in US. And we are mostly focused on access networks, but we look at the integration and co-integration of optics as a generic solution. So we are basically on the value chain. We are distributed almost on the optical and electronics part, and also on the manufacturing, because we have also manufacturing capabilities. And we aim at closing the gap between fab and mass production in terms of the photonic integration. So we take PICs from the design to the fabrication side. So we have been exploiting a lot of the technologies available from electronics and ASICs and the other technologies, and we saw that there are, of course, advantages in all of them. And then there we see that we need an effort, and that's what we have been trying to bridge with a set of machines and process and workflows that we have developed by our own, and also by other of the partners that already have been presented here. And we can result in these hybrid approaches, which can then solve some of the problems that we are facing, like merging electronics with photonics, soft aligning fiber vias to make the packaging faster, or coupons on top of chips, or even co-integrated electronics with photonics in order to get the best out of the system. So with that, we merge into the final product. So that's kind of like 3 examples of where we have the photonics basically on the same line of the electronics, and solving our problems of the pluggables and the modules in terms of their interaction with the external world from the electronics and the photonics part. So thank you. Was quite fast. Hopefully enough clarity.
Great. Thank you so much, Antonio, for bringing to an end a fantastic meeting. Thank you to all the speakers. Together, these perspectives underscore the collaborative engineering and ecosystem alignment required to transition co-packaged optics from prototype to production. So as I said, it's now time to close the meeting and say goodbye to those on YouTube.